Hello everyone, I'm Shweta. I'm an assistant professor at ETH Zurich, the other side of the country. And today I'm here to sort of present a very courageous view of the world that we are yet to see. And take this with a bag of salt. Be careful what you listen to, right? So I always like to start my presentation with some threatening data. I've been giving this talk for the last 2-3 years, and every year I have to update this number. And in the last 2-3 years, I can tell you the number of records that are being leaked due to data breaches is increasing linearly, right? So I started with some 13 billion, and then last year I gave this talk, it was 22, and last night I had to change this to 40, right? And if you do this math, it's almost like every year you end up losing all of your data, right? So what's the point of protecting data at this point? And if you try to think about why, right, beyond the hype of, oh, everything gets attacked, one line of reasoning has been, look, I mean, everyone is writing so much code these days, right? Everything you interact with is written in code, and the more code you write, it's going to have bugs and issues, right? And so again, going back to the data, the number of bugs that we see in complicated pieces of code, right? So here is an example of Linux, which is sort of an operating system, which most of the devices you use runs, right? And it's getting larger in size, but it's also getting larger in the number of bugs. And it's not special to Linux. If you take another piece of complicated software, hopefully, which you have never heard of, which runs in the cloud, it's smaller in size, 500,000 lines of code, but it's also following a similar trend, right? And every now and then you see this red bump, and you may ask why, and that why is because, oh, that year, security researchers were very interested, and they paid special attention to the software and ended up finding more bugs, right? So there are more bugs than we have discovered. And this is all fine, right? Yeah, 3-digit numbers for bugs, billions of data records leaked. What can we do about this? If you take a look at how the software runs, let's say you are as excited as me and you want to do genome analysis of your data, and you get it in a file, and now you want to see what kind of diseases you're prone to and so on. You want to run it on your machine, but it's not powerful enough, so you go to the cloud. And you're diligent, you encrypt your data, right? You send it over encrypted channel to the cloud, and make sure you run it in your own account, right? So this is nice. You're using encryption, a sophisticated technique to make sure your data is safe. But in the end, the application is going to read that data and process it. So what is the amount of code you're trusting? At this point, at least knowingly, you're trusting 50,000 lines of code. But little to your knowledge, there is an entire software stack underneath, which you kind of are not supposed to be aware of, which is called the operating system and the hypervisor. And remember the last slide I showed you, that's those guys, right? And the issue is you might use encryption, you might even use privacy-preserving methods, but at the end of the day, it's going to run on some software written by someone else. And this is large software, right? This is millions of lines of code, which you do not have any control on. And attackers are smart. They are not going to try and break the encryption. They're just going to go a layer below, find a silly bug in this large piece of code, and compromise you, right? And the math, again, is not in your favor. The size of the code is large, so every day they'll be able to sort of attack you. This is a very pessimistic view of the world, although reality, right? And I'm here to come to give you a good news, right? So let's think about, if we had a chance to redo this a little bit, how would we do this, right? There is no denying that you have to trust the analytics application. Let's just make peace with that for now. It's few thousand lines of code. You can trust your doctor or whoever, so you can also trust this small piece of software, right? And what you would want to do is have a guarantee that you want to run this in a container, right? Sort of like your own personal environment where no one else is able to look at what's happening, right? This is great. How do you do this? You have to sort of anchor your trust in the hardware. This is what some of the things which Cedric was saying earlier tie into, right? And today, hardware has become modern enough that it allows you to do this. But what's the what's the big advantage of this, right? The big advantage of this is you can now still have all this untrusted piece of software, right? The one which is letting you talk over the network, the one which is letting you, get your status updates and so on. But you don't have to trust that software, right? Hence, it's all in gray or blue. And the nice part is you only have to trust your application and the hardware. Rest of the software stack can become or stay as buggy as it is. So this is great. Any bug that you see now is not going to affect you, so you're happy. The other upside to this is that you're reducing the amount of code you're trusting, right? Instead of trusting millions of lines of code, now the number is 20,000 lines. As a computer scientist, why is this small? Because now I can give mathematical proofs about the correctness of this code, so you can get guarantees that not only will it have bug, but it's also doing the correct functionality and so on. Right? So reducing this number to a smaller size is important for better security. Right? And again, at the end of the day, you're going from trusting millions of lines of code to a few thousand lines of code. Right? And so just to put this side by side to contrast, this is where we are, where trust flows downwards. You basically are asked to trust whatever code. And you're going more towards a controlled environment where you say, hey, I trust this software. I'm going to run it in my environment. And yeah, I have to trust the hardware. So that at least gives you a much better confidence about what you're running. And then all the other sophisticated techniques like verifying what the software is it coming from the legitimate provider, is it the right version, and so on, become more tractable if the numbers are smaller. Right? So this sounds a bit too good to be true. How does this exactly work? Right? And so this goes back to two key pieces. One is you have to trust the hardware. And today that means trusting either NVIDIA, ARM, Intel, or AMD. Right? The good news, though, is that when you're running all of this in the cloud, you do not have to trust the cloud service provider, in our case, let's say Microsoft or Google or Amazon. Right? All they have to do is procure this hardware from these providers, put them in their data centers, and they can run whatever operating system or hypervisor they want, and you're ensured that your code and data stays safe. Not even the cloud service provider is allowed to access it without getting detected. Now, this is great, right? This is way, way better than the dire picture we painted earlier, right? And better yet, you get small code sizes, right? So you can formally verify this. You can say, I know mathematically that this is whatever happening is correct. And you only have one entity to blame if anything goes wrong, either yourself or the hardware provider, right? This is much better than trusting n parties. Now, I've been doing this for the last 5-6 years. When I started, only I think Intel and ARM were the main players, and last week NVIDIA has jumped into this scene, right? So it seems like hardware providers are super excited for this opportunity. So are cloud service providers, right? So definitely there is enough impact and adoption. This is not a pipe dream, right? So this was my view until I came to ETH and started talking with folks at ICRC who painted a very, very realistic picture for me, right? So I was like, oh, yeah, you can run your web server, you can run your data analysis, everything is secure, I am happy, right? Not so much, right? So if you go to ICRC, the stakes are much, much higher, right? So instead of doing genome analysis, you could be doing something as simple as just taking data of refugees and trying to find where their relatives are, right? Now, just getting this data to the cloud is difficult. On the ground, people need to have similar devices which are protected, because on the ground, someone can just snatch their phone and start looking through their data or tamper with it, right? So the data has been contaminated even before it hits your cloud server, right? So that on-ground effort itself is a big undertaking. Similar principles apply, right? These things can also run on mobile phones. If you are, for example, running Android or Apple, your biometric data is protected by similar technology, right? But it doesn't protect you against a coercive adversary who's going to, snatch your phone, force you to show your face or biometric data, and then steal or tamper with your data, right? However, having this secure container helps you protect sensitive data once it is in the cloud, right? You can do functionality like run AI and ML models, like Cedric was just saying. Now there is support for accelerators. So if you're doing searching and finding, let's say, based on pictures, this is now much more secure than doing it over plain text, right? The bad news is the software is least of your concerns, right? Now there are nation-state adversaries and coercive environments where people can simply barge into the data center, force your employees to open the servers and so on. Again, this technology helps because it was built with the assumption that you don't trust, let's say, the cloud service provider. So even if someone comes in physically and tries to tamper with your hardware and so on, the guarantees still uphold, right? So this is nice and sort of positive. The last piece in the puzzle, and this is we're really grasping for straws in terms of finding out problems, is do you really trust the hardware, right? The 4 companies that I showed you are yes, we trust it, but would anyone else, right? There's also a question of will these technologies be adopted in the rest of the world? Intel, for example, the source code is not open source. You can't look into it. You have to blindly trust the hardware. It's same for all the other 3 companies that I mentioned, right? And so when it comes to use cases such as ICRC, this may not be enough, right? It may not be enough to just say, oh, I trust Intel or I trust NVIDIA. We may want to do a bit better, right? Again, I come bearing good news. There have been open source initiatives in terms of building trustworthy hardware. This is something what we do at ETH, right? And this is where we are trying to see whether you can use these technologies to build this stack in a more trustworthy way. Right? So the upside is you have open source hardware, which is available to scrutiny for everyone. It's also open in the sense if tomorrow you want to build it in your own foundry, you can do that. Right? So it's open in both senses. Right? And because we have control over this hardware, we can decide how to design it. We can make it more modular. We can bring in more diversity to make sure that if one attacker is compromised, then the entire hardware is sort of not backdoored. Right? And so slowly over the year, starting with a very difficult goal, I think with the help of ICRC, we've been able to move this forward and sort of paint a picture where this doesn't seem as difficult as we seem, at least from the technical point of view. Right? So this concludes my talk, and if you have more questions, contact me. Otherwise, I'll be around for the panel. Thank you.